Welcome back to our second video series on systematic reviews and meta-analyses, where we are going to be applying our knowledge of SRMAs in the critical review of one. In this second video, we are reviewing the conduct of the meta-analysis and recording information which we will be using in performing a brief grade assessment in the third and final video of this series. So take out your SRMA and worksheet from video 1 and let's continue on from question 11. My only disclosure is that I am currently a MyTax Elevate postdoctoral fellow jointly funded by the Government of Canada and the Canadian Sugar Institute. As a reminder, in the first video of how to read SRMAs, we reviewed how the systematic review component was conducted in our selected SRMAs. The example we are using in this exercise is entitled Food Sources of Fructose-Containing Sugars and Glycemic Control, a systematic review and meta-analysis of controlled intervention studies, and was published in the British Medical Journal in 2018. I encourage you to continue with your own selected SRMA. However, if you want to use my example to follow along, you can find it on the CSI website under the links to the videos for this series. Please remember you will need the online supplement or appendix as it contains important information. The worksheet I have created for us to use to make notes on throughout this exercise is also found on the CSI website under the video links. Now moving on to reading and reviewing the meta-analysis component of the SRMA. Again, as a reminder, a meta-analysis is a statistical technique for combining the findings from several independent studies to resolve discrepancies and provide a quantitative estimate of the treatment effect. Here are some general steps in performing a meta-analysis, which I discussed in the first series of videos. Now let's see how each was conducted and reported in your SRMA. There are different statistical software packages which can be used to run the analyses. Two common ones are Review Manager and Stata. Check to see what statistical method was used for the meta-analysis conducted in your SRMA. In my example, Review Manager was used for primary analyses and Stata for subgroup, dose response, and publication bias analyses. Before we take a look at the results of the primary analyses, look at what data was extracted from the included studies. Recall that the data used in a SRMA depends on the type of studies, clinical trials versus observational studies. Clinical trials have mean differences, which if you are pooling data using different units that cannot be converted to the same unit, you then use standardized mean differences. This is in contrast to observational studies, which usually report relative risks. To keep things simple, my example uses clinical trials and thus mean differences. To find out what information is being extracted and analyzed in your SRMA, you can see this in the methods, but also in the forest plot, which I have taken a snapshot of here from my example. Take a minute to look through your SRMA and record in question 11 in your worksheet whether your SRMA reported mean differences, which you may see reported as the abbreviation MDs, standardized mean differences, or sometimes SMDs, or relative risks, which can be presented as RR. Now let's take a look at the primary analysis and see what the overall total estimate of the effect was found to be. Firstly, note that not all results figures will be presented in the same way. For my example, in Figure 2, they actually presented a summary plot, which presents each of the 4 individual analyses that were conducted for the 4 different levels of energy control pre-specified. Looking just at the results for substitution studies, there is a summary effect estimate presented for each of the food sources and then a total overall effect estimate. This total overall effect estimate is the primary analysis result for the substitution studies. We look at this for the overall result, which is that there is a significant reduction in hemoglobin A1C of minus 0.22%, resulting from fructose-containing sugars compared to control. The full forest plot for the substitution studies is presented in the supplement as supplementary figure 2. Here we can see the effect of each individual study and then the overall total effect estimate at the bottom. Notice that this result matches what is presented in the summary plot I showed you in the previous slide, as it should. Take a minute to find the primary results of your SRMA. This will be presented in the text as well as in a figure. Record your finding in question 12 in your worksheet. As a reminder of how to interpret the forest plot, first take a look at the scale at the bottom. The 0 means that there is no difference in outcome, whether you are given the intervention or the control. To the left means that there is a reduction, and to the right means that there is an increase in the outcome when given the intervention compared to the control. So if we're talking about HbA1c as the outcome, then studies to the left of the line of no effect show a reduction in HbA1c when given the intervention compared to the control. Conversely, studies to the right of the line of no effect show that there is an increase in HbA1c when given the intervention compared to the control. Now we will take a look at heterogeneity in the main analysis and whether there were strategies undertaken to try to address it. Recall that heterogeneity is a statistical test done which assesses whether observed differences in results between studies are the result of chance alone or if they may be the result of variability in the included studies themselves. Remember that variability between studies can result from clinical differences, like different populations of each study, or methodological differences, like the study designs, for example, crossover versus parallel studies. Remember our classical example of heterogeneity, where we have two studies with opposite results. The heterogeneity in this example is 98%, which is found beside the I squared, and means that the variability in the included studies is most likely not due to chance, but due to diversity between the studies themselves. Thus, we want to perform sensitivity and a priori subgroup analyses to try to see if we can explain the heterogeneity. So we are looking for the I squared, along with its p-value, in the forest plot to see what the heterogeneity of the analysis is. And the higher the I squared, the more likely that differences between studies are not due to chance, but diversity between the studies themselves. In the summary plot in my example, which is figure 2, heterogeneity is presented to the right of the forest plot. Looking at the total, I can see here that the heterogeneity of the overall total effect estimate is 82%, which is considered substantial and is significant with a p-value for heterogeneity at less than 0.001. Again, if I look at the complete forest plot for the substitution studies on HbA1c in supplementary figure 2, I can confirm the heterogeneity. Now I want to look for the results of a sensitivity or a priori subgroup analyses that we found described in the methods earlier. Take a minute to look for the heterogeneity in your SRMA and take note of it beside question 13 in your worksheet. Let's take a second to reflect on this information. Does your main analysis have substantial and significant heterogeneity? Record your response in question 14 in your worksheet. Recall that heterogeneity is considered substantial at an I² greater than 50% and is significant at a p-value less than 0.1. The next step we want to take is to explore the sensitivity and subgroup analyses, which we planned to try to explain heterogeneity. Here is the text of my example, which describes the results for the explorations into heterogeneity. However, neither the sensitivity analyses nor the a priori subgroup analyses explained the substantial heterogeneity found in the main analysis. Check the text results of your SRMA, where sensitivity and a priori subgroup analyses results are presented, to see whether the authors describe if any heterogeneity, that is, if it was significant in the analysis, was explained. And make a note of whether any significant heterogeneity was found in the main analysis, and if so, whether or not it was explained by sensitivity or subgroup analyses. Then you can record your notes in question 15 of your worksheet. Beyond the text, you will likely find results of the sensitivity and subgroup analyses in figures and tables. Here is supplemental figure 6 for our example, in which we can find the a priori subgroup analyses for substitution studies on HbA1c, which is what we are focusing on in our example. None of these are significant. In this column here, you can see what is called residual heterogeneity, which is the heterogeneity which remains after accounting for any effect modification by each subgroup. The residual heterogeneity in each of the subgroup analyses in this example remained at about 80%. Thus, none of the subgroups seem to have any effect modification on the substantial heterogeneity in the main analysis, which was 82%. Quickly, let's take a look at whether dose-response analyses were conducted and what the results were. So for my example, there was no significant linear dose-response effect. However, there were some interesting results in the nonlinear dose-response analyses. In this example, they performed dose-response analyses using various cut points recommended for free and added sugar intake. The World Health Organization, among some other organizations, recommends less than 10% of energy to be consumed as free sugars. The largest reductions in HbA1c were seen only at doses up to 10% of energy, and no dose-response effect is observed beyond 10%. As the authors note, there may be a benefit to recommendations of no more than 10% of energy from free or added sugars. However, there are no further advantages at the other public thresholds of less than 5% of free sugars. Take a note of whether dose-response analyses were conducted in your SRMA, and if so, what the results were. Record your findings in question 16 of your worksheet. Next, let's take a look at whether risk of bias was addressed in your SRMA. First, we will see if assessments on individual study quality were performed. There are different tools that can be used to assess study quality. Some examples include the Cochrane Risk of Bias tool for clinical trials, the Newcastle-Ottawa score for observational studies, or the quality assessment tools provided by the National Heart, Lung, and Blood Institute. The second item in our review of risk of bias assessment is looking for whether publication bias was assessed. Just a quick reminder of the importance of these steps as you want to understand the quality of the data in which you are drawing your conclusions. Remember, garbage in equals garbage out. If your SRMA used the Cochrane Risk of Bias tool, here's a screenshot of the Cochrane Risk of Bias tool 1, which outlines each of the domains which are assessed, including sequence generation, allocation concealment, blinding, incomplete outcome data, and selective outcome reporting. There are a set of criterion used to assess each, and unfortunately, we don't have time to go through how this is conducted, but each is assessed for each individual study and determined to have either a low risk of bias, high risk of bias, or unclear. Note that Cochrane recently released an updated version called the ROB2, which you may come across in the use of for more recent SRMAs. Here's the risk of bias summary of all studies in my example, which is found as supplementary figure 1. As you can see in the figure legend, green represents assessments of low risk of bias, yellow is unclear, and red is where assessments were made indicating high risk of bias was found. In this example, there's a bit of red representing high risk of bias in the domains of random sequence generation and allocation concealment. From the table of study characteristics, I know that approximately 25% of studies were not randomized, which explains the approximate 25% of high risk of bias in these domains. However, note that this figure is based on all studies included in all the analyses. That is, it includes the analyses of all the other outcomes. Thus, to get a better sense of the individual study risk of bias for my outcome of interest, HbA1c, I look for the risk of bias assessments presented from each individual study in supplementary figure 2, where this SRMA presents the data within the forest plots in the far right-hand column. Sometimes the risk of bias data for each individual study can be reported in its own figure. In this figure, on HbA1c in substitution trials, overall, I can see that there is very little red, and thus very little high risk of bias was identified. Risk of bias assessments can also be used to complete subgroup analyses where you compare those studies at high risk of bias to those at low or uncertain risk of bias to see if the results differ significantly and whether this affects your interpretation. Looking at supplementary figure 7, as you can see in the far column to the right, none of these subgroups were significant. So risk of bias did not modify the effect, nor did any of these explain the substantial heterogeneity. As you can see here, all the residual I-squareds are still around 80%. Make a note on whether risk of bias was performed in your SRMA. And if so, was there a lot of high risk of bias ratings? If any subgroup analyses on risk of bias were performed, did they indicate that studies with high risk of bias were different from the others? Depending on the tool that was used to assess individual study quality, the results may be reported as comparisons between studies rated as low quality versus those rated as high quality. Record your findings in question 17 in your worksheet. Now on to the last aspect to assess, publication bias. Recall that to assess publication bias, you must look for the funnel plot of the studies to assess for asymmetry. As a rule of thumb, tests for funnel plot asymmetry should be used only when there are at least 10 studies included in the meta-analysis, because when there are fewer studies, the power of the test is too low to distinguish chance from real asymmetry. The funnel plot is a plot of each study by their effect and variance, and the solid line represents the overall pooled estimate of the effect. Then look for the statistical tests for publication bias, known as the Eggers and Beggs tests. And these are interpreted as significant at p less than 0.05 and sometimes some metas use p less than 0.1. So check to see what was used in the methods of your SRMA. Note that if there is asymmetry or significance in the statistical tests, what this may mean is that there are some small studies typically favoring the control that are missing, meaning that they have not been published. From my example, the funnel plot is presented in supplementary figure 26, and in the top right-hand corner are the Beggs and Eggers tests. Note that there is no obvious asymmetry, and neither of the tests are significant. So we conclude here that there is no publication bias. Check your SRMA to see whether publication bias was conducted and whether it was significant. If it was significant, were methods completed to address publication bias, like the trim and fill method, which I briefly discussed in the previous video series. Record your findings in question 18 in your worksheet. We have now come to the end of our worksheet and critical review of our SRMA. In the next video, we will use the data we've recorded to perform a rough grade assessment to get a sense of the certainty of evidence. Thanks for participating and hope you join again in the next video.